Bismillahirrahmanirrahim. Welcome to lecture number 14 of Advanced Computer Architecture. Today we will discuss error correction. The discussion agenda is we will study why do we need error correction. We will discuss one basic algorithm of error correction, that is Hamming code, and we will discuss how do we implement error correction in hardware. So there are two types of failure. One is hardware failure and one is soft failure or soft error. So hard failure means that the physical device is permanently damaged. Memory cell or cells, they are affected. Those cells that are affected cannot be able to store data, but become stuck at 0 or 1 or switch erratically between 0 and 1. This hard failure can happen because of harsh environmental abuse, manufacturing defect, or wear and tear. The software, these are random non-destructive event that alters the contents of one or more memory cells. No permanent damage to the memory, and it can be caused by power supply problems or alpha particle. This is what error correction code function works. So for example, we have data n, let's say this is m, and we have a function, let's say, that produces code k, and we store this in memory, and then we compare m, and from the m we produce a k, and the k that is stored in the RAM. We compare both the k. If they are the same, it means we are able to correct the data. If they are not the same, so then it means that there is error in the data. So this is how Hamming code works. For example, we have this three circles, and the intersection point contains data. For example, in circle A we have 1 1 1, in circle B we have 1 1 0, in circle C we have 1 1 0. So then within the circle we add the number of ones. Number of ones is only one bit we can add, but we add a bit so that the number of ones become even or odd. So if we are using even parity, so we want the number of ones to be even. If we are using odd parity, we want the number of ones to be odd. So assuming that we are using even parity, so the number of ones is like 1 1 1, and we add another 1 to make it even. Similarly, in circle B it's 1 1 0, so the number of ones is already even, we add a 0. And similarly in circle C we have 1 1, the number of 1 is even, and we add a 0 here. So assume that the data we receive is something like this. You see this 0 is changed than this one. The rest is the same. But how do we know there is error? We look at this circle and we see it's odd, but it should be even. It means some bit is wrong. Which bit is wrong, we don't know. Then we look at circle B, it's even, that's fine. We look at circle C, it's odd, but it should be even. So it means that this bit is wrong. So this way we know that what bit is in the error and how do we correct it. So the number of bits, how many bits are used to correct the data. So if we have 8 data bits, we need 4 check bits. This check bit is represented by k, and the data bits are represented by m, and 2 power k minus 1 should be greater than or equal to m plus k. So the data size increases. For example, if we have 256 data bits, we just need 9 bits. And the percentage increase is 3.52. It's very small. Here it's very big. But as we increase the data size, we have very small. And single error correction, double error detection. So for this is only single error correction, but no detection. No double error detection, but here we can detect double error and we can correct single error. So it's only one bit is increased, and the percentage increase is 3.91, but we are able position. So check position is as we discuss in this table, We have 8 data bits, so we have 4 check bits. So these are our 8 data bits and 4 check bits. The position is known as, for example, all those positions that contain 1. So this is like 2 power 0. 2 power 0 is 1, so that is check bit. 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8. And the position of the data bits is this one. C1, C2, C4, C8 are computed like this. D1. So see, how do we compute C1? We add all those bits that contain 1 at position number 0. So for example, it should be D1, D2, D4, D5, D7. Similarly, C2, those bits that contain 1 at position number 2. So D1, D3, D4, D6, D7, and so on. So this is the data. These are our data bits, and the C1, C2, C4, C8 is computed as 1. C1 is 1 because of 1, 0, 1, 1, 0. Exclusive OR together becomes 1. Similarly, C2 value is computed, C4 value is computed, C8 value is computed. So then this is what data we store, and when we retrieve the data, we find that there is an error at this position. So how do we compute there is an error? We check them again. The value of C1 should be 1. It's the same as this one. C2 is change. C4 is change. C8 is the same as. But how do we know which position is change? We exclusive are C1, C2, C4, C8, the one that is stored 1, 1, 1, 0, 1, 1, 1, 0, and the one that is retrieved 1, 0, 0, 0. If you exclusive are, it's 0, 1, 1, 0, 0, 1, 1, 0 is number 6, and this is the bit that is changed. So using Hamming code, let's take an example of single error correction and double error detection. We are able to fix only single error, but even if there are double errors, we are able to check with this algorithm. So let's assume we want to process this sequence of bits. We use even parity. So with this circle, we add 0. For this circle, we add 1. For this circle, we add 0. And we add a 1. An 8-bit is used to add the even parity for all the number of ones. So there are total 3 ones, and we add a 1 to make it even parity. And then when we retrieve the data. So this is what we store, and when we retrieve, 2 bits are changed. This bit is changed, and this bit is changed. Now we check this parity. It's even, it's odd, and this is odd. So it should be even. So it means the intersection for this and this, because this circle is correct, and the intersection of these two is this one. So it means this bit needs to be changed. And when we change this bit to 1, this is not what we store. We store something this one, right? So here is even parity, even parity, even parity. But this one is changed. Now this is not even because there are 4 and 1. So this extra bit is used to detect even parity, to detect double error using the even parity, because you just saw that when there are 2 errors, so the single error correction is not able to detect it. It replaces an incorrect bit. So most commonly, semiconductor memory is equipped with single error correcting, double error detecting code. Such code require 1 additional bit compared to SEC. This is what we saw in figure table 5.2.